Welcome back. Today we want to talk about transforming graphs. So I'm fairly certain that you've seen some of this in the context of lines and parabolas, and I'm going to attempt to connect those things together. So if I have sort of graph of a very basic parabola, this y equals x squared thing, then hopefully you have seen at some point in your past that if you take this and you were to turn it into the graph of y equals x minus 3 squared plus 1, perhaps, and then put a 2 in front of it, then what that would do is it would move the vertex to 3, 1, meaning it would move the graph 3 over and 1 up. And this would cause the y coordinates to stretch by a factor of 2. And so your graph would end up taller, or perhaps you could think of it as skinnier, and it would move over 3 and up 1. So it should look something like this. You would have 3, 1, and your parabola would be twice as tall. So we can confirm this really quickly using a graphing utility. I can say, what if I have y equals x squared, and what if I have y equals 2 times x minus 3 squared plus 1? And I think you've seen me do this in the first lecture. So there we have it. We are twice as tall, though it's hard to see in this, and then we're over 3 and up 1. Okay, so far all of this is good. In order to advance this discussion to the general type of graph, let's consider this thing. It's a semicircle, and it turns out the equation of this semicircle is going to be y equals the square root of 1 minus x squared. If you already know y, great. If you don't, that's not a problem. You're not responsible for knowing this equation yet. So on the screen, you can see that if I graph y equals root 1 minus x squared, it is indeed this shape. What we're going to try to do is manipulate this shape. So let's imagine I want to take this graph, and I want to move it to the right 3 and up 2. So I want this point to end up right there, and then everything to be relative to that. So that phrasing makes me think I want to construct a brand new coordinate system with its origin right there. And I'm going to label this coordinate system with capital Y and capital X instead of lowercase x and y to distinguish them. And so perhaps if I want to make the graph right here, that I can convince you in this coordinate system, I have 1 and -1, just like I have 1 and -1 here, and I have 1 up here. So the relationship between capital X and capital Y should be exactly the same as the relationship between lowercase x and y. I should be able to write this graph as capital Y equals the square root of 1 minus x squared. After all, it's the exact same shape. Okay? But now, I would like to say, what if I want to express this red graph using the pencil coordinate system? So I need to now establish a relationship between lowercase x and capital X, then lowercase y and capital Y. But this is not so bad, because I understand that whenever lowercase x is 3, capital X is just getting started at 0. And they advance 1 by 1 because they are the same size coordinate system. So I can say that lowercase x is always going to be 3 more than capital X. When capital X is 1, I just add 3. When capital X is -1, I add 3. Because when lowercase x is 3, capital X is 0. Okay? And I can do the same exercise with y. I can say that lowercase y is 2 when capital Y is just getting started. So lowercase y should be capital Y plus 2. Now, this allows me to then solve for capital X and say capital X is simply lowercase x minus 3, and that capital Y is simply lowercase y minus 2. So if I desired to express this relationship using the pencil coordinate system, then I would simply say replace this for that, that's substitution, and replace this for that. So in the pencil coordinate system, we would end up saying y minus 2 equals the square root of 1 minus parentheses x minus 3 squared. And it's customary for us to solve for y, so why don't we move the 2 over to the other side, and it will look like this. And perhaps this is something recognizable. You might have been told at some point in the past that putting x minus 3 means you're going to shift the graph to the right 3 units, and putting a plus 2 outside means you're going to shift the graph up by 2 units. Let's test that theory. We're going to go in here. We're going to make a new graph, y equals the square root of 1 minus x minus 3 in parentheses squared with a plus 2 at the back. And indeed, we have moved this graph over 3 units and up 2 units, simply by considering a new coordinate system and doing a change of variables. In order to consider dilations, we're going to think about a coordinate system where the origin stays in place, but we're going to make the tick separation. So here in the lowercase x coordinate system, there's 1, 2, 3, 4. But in the capital X coordinate system, let's make the ticks twice as far apart. So we're going to say this is where capital X is 1, this is where capital X is 2, this is where capital X is 3. So every time lowercase x goes up by 2, capital X only goes up by 1. Perhaps then we can say the relationship is lowercase x is always going to be double of capital X. Okay. Now for the y-axis, let's construct a y-axis with capital Y, and we're going to say those are going to be 3 times as far apart, the ticks are. So I'm going to say 1 goes here and 2 goes here. So every time lowercase y goes up by 3, capital Y is going to go up by 1. So lowercase y is going to be 3 times capital Y. Now, if I were then to take this shape and I wanted to graph the relationship y equals the square root of 1 minus x squared using the capital X and y coordinates, then I would end up saying, well, it's going to go from -1 comma 0 to 0 comma 1 to 1 comma 0, and it's going to have this kind of shape. So you see, we've achieved our goal of stretching out the graph by 2 times along the x and stretching it out by 3 times along the y, and this is that dilation. So we can take this like we did before and solve for capital X. Solve for capital X is equal to 1/2 lowercase x, and solve for capital Y equals 1/3 lowercase y. And then we can perform these substitutions in there and say the graph that is presented in red can now be written in the pencil coordinate system as replace capital Y with 1/3 y and replace capital X with 1/2 x. And then it's customary to solve for y, so we can say y equals, multiply the 3 over, like this. And let's see what that looks like. So we'll have 3 times 1 minus, parentheses, 1/2 x, and then I want that whole thing to be squared. So I'll go ahead and say 1/2 times x, put it in parentheses, and square this. Hit that button. And that is exactly what we see. We've stretched it out by a factor of 2 along the horizontal and a factor of 3 along the vertical. Now, let's combine these ideas. So I have my default coordinate system x and y, and perhaps what I want to do is I want to make a new coordinate system where I'm going to stretch the x out, stretch the y out, and then shift the entire coordinate system toward the upper right. So what I'm going to end up with is something like this, where I have a capital X and a capital Y. And what I'm going to say is on this capital X and capital Y coordinate system, I'm going to have 1, 2, 3, 4, 1, 2, 3, 4, like this. And the gap here, so this gap in the pencil coordinate system is going to correspond to a gap of B, and then this gap right here is going to correspond in the pencil coordinate system to a gap of A. Okay. And this origin right here is going to move in a way that I'm going to translate C units toward the right and D units up. So if I combine all of this, I want to say that in order to rewrite something from here into my pencil coordinate system, I will say for every 1 on the capital X, I'm going to have to use B units in the lowercase x. So the lowercase x will have to be capital X times b. But then when all of that is said and done, I need to say, oh, but since lowercase x starts at c, I have to add c to my result. Okay, so b tells me I'm going to stretch out by b, which means every time I count up by 1 for the capital X, I have to multiply that by my gap b. And then I finally have to shift it by c so it looks like this. Similarly with the y coordinates, I can say if I take my capital Y, each one along that red axis represents a units along the lowercase y axis. So that would be a multiplied by each one along the capital Y. And then finally, I have to move up by d, so I would get this. All right, so now, if I were to graph, for example, this little semicircle right in here, and this semicircle might be from -1 to 1 and then 1 up here. Okay. Now, if I were to put that in this coordinate system, I would have from -1 here to +1 along the capital X, and then this would be up here at capital Y equals 1. And keeping in mind, this is going to be a relationship between capital Y and capital X. But ultimately, it's the same type of relationship. It's the same shape. I've just placed it in a new coordinate system that's stretched out and shifted. Okay. So I want to take this and replace the capital Y with this capital Y and replace the capital X with this capital X, which requires me to solve for those. So I'm going to solve for capital X by saying first subtract the C. Then I have to divide by B. So I would have this situation. And then to solve for capital Y, I would first subtract D, and then I would divide by A. This is what I would have. And so, if I perform a substitution, this will show up there, and I will have 1 over A times Y minus D is equal the square root of 1 minus, in parentheses, 1 over B, x minus c, all of this, right? Because I'm taking this and substituting for all of that. Now, it's perhaps customary to solve for y in this position. So maybe I'll say, well, let's multiply both sides by a first. So I'll have a times this business. And then finally, when I'm done, I'll add d to the other side. And this is what it will look like. And so this becomes sort of a formula for a generic coordinate transformation where we're taking a graph and we're stretching it out in the x and the y, and we're shifting it in the x and the y. So in this case, I stretched it and I shifted it to the right and up. So perhaps you could argue that a and b are numbers bigger than 1, and then c and d are positive numbers. But does that always have to be the case? No. If you make a 1/2, for example, you would end up compressing this y-axis, so you would make everything half as far apart, which would squish your graph vertically. So if a is less than 1, then you would have what we call a vertical compression, and if this b is less than 1, then we would have a horizontal compression. Now what if a and b are negatives? Now that requires a dilation where you take the axis and make all the values negative. So you would actually flip the x-axis backwards. So if you were to put a negative number in for b, you would end up taking your graph and flipping it horizontally across the y-axis. If you made a negative number, then that would force you to dilate your y-axis to be upside down, and that would then allow you to reflect your graph vertically over the x-axis. And if c and d were negative numbers, then that would just mean you're shifting to the left if c is negative, or down if d is negative. So that is the overall picture of linear transformations of graphs. All right, let's consider some examples. So on the screen, you see a graph of y equals square root of x, and we want to take this through a few transformations. So let's say we want to reflect across the y-axis. And then we want to do a vertical dilation, multiplying by 3/2. And then let's do a translation where we're going to move to the right by 5 units and down by 2 units, let's say. Okay. So what we really need to do is we need to take our x-axis and point it backwards. That will flip us across the y-axis. Then we want to take our y-axis and stretch it out 3/2 times. Okay, but then we want to take that coordinate system and move it to the right 5 and down 2. So this point right here in the pencil coordinate system would correspond to 5 and -2. And this will be the origin of our new capital X, capital Y coordinate system. So we need the x-axis to point toward the left. So I'll point it like this. This is capital X. And our y-axis, capital Y, is going to point up. But the gaps, every time capital Y goes up by 1, that gap over here is going to be 3/2 units. Okay, and then in this case, the x is going to count backwards. So that's going to be 1, 2, 3, 4, 5, like that. And it's going to count in the negatives going that way. All right. So our goal is to, number one, produce the graph that's on the screen in the red coordinate system. So we see on the screen, that's 0, 0, that's going to be right there. And then the next point, it turns out it's going to be 1, 1. So I'm going to have this. And then the next point that's really easy to look at is 4, 2, because the square root of 4 is 2. So if I go 4, 2, I'm going to be all the way up here. And then if I connect the dots, something like that. Okay? So hopefully you can trust me that we've reflected across the y-axis, and then we've done a vertical dilation of 3/2, meaning we stretched it 3/2 in the vertical direction, and then moved 5 over and down 2. So in order to figure out how to do the equation for this, we want to ultimately say that this is a graph of capital Y equals the square root of capital X, right? We've produced the same relationship in the red coordinate system. But we have to decide how to relate the capital coordinate system with the lowercase coordinate system. Well, by our logic earlier, lowercase x it's a reflection, which means the capital X axis points the opposite direction. So all of my lowercase x values are just the negative versions of capital X, right? However, after I've done that, I have to add 5 because I've moved my coordinate system over to the right by 5. So let's check that, right? When capital X is exactly 0, then lowercase x is exactly 5. And when capital X goes up by 1, meaning this way, this way, this way, every time capital X goes up by 1, lowercase x is going to reduce by 1. Okay, consistent. Then we go to lowercase y. So lowercase y is going to be 3/2 times spread out. So I'm going to say 3/2 times capital Y, meaning every time this goes up by 1, my lowercase y will go up by 3.5. And the starting location, so this point right here, is -2 on the y-axis. That's the -2 right here. So when capital Y is 0, that's the origin of the red. My lowercase y is 0 minus 2, which is -2. Okay, so far so good. This is consistent with what we did earlier. Now, in order to make substitutions, I require myself to solve. So I would subtract 5. So I'd say lowercase x minus 5, but then I would have to divide by the -1 to get capital X isolated. To get capital Y isolated, I would take y, lowercase y, plus 2. Then I would divide by 3/2, which would put this at 2/3, and this would be capital Y. Now, if I perform the substitution, I will end up with 2/3 y plus 2 equals the square root of negative, parentheses, x minus 5. And if we want to solve for y, as is tradition, we can take this and reverse it. Y equals 3/2, like this, minus 2. Now perhaps you're looking at this and saying, wait, I feel like we're undoing what we just did. This seems redundant. We wrote it like this, and then we solved for capital Y, but then after we plugged it in, we solved for lowercase y again. And so it turns out that if you go through the transformation and you go through the inverse transformation, it just so happens that this right here is just capital Y, isn't it? Because capital Y is the square root of capital X, and we perform the substitution in here. So we can just jump directly from here to the final form by just taking the capital Y, switching it out for whatever the relationship is, and then taking that and switching it out for what uppercase X is. But at the end of the day, what we want to look at is, what is the original structure or original relationship in this? Well, it's the square root. We often call this a parent function or a parent relationship. So that's the one that's displayed on the screen. And then from that parent, we're going to say, okay, we've manipulated the x's in here. How have we manipulated the x's? Well, that negative in front told us it was going to be a dilation by -1, meaning we've reflected over the y-axis. And this -5 is going to tell us we're going to move toward the right 5. And then outside of that, these are going to be from this transformation of the y-coordinates. The 3/2 in front means we have multiplied the verticals by 3/2. So we stretched them out, and we've subtracted 2, so we've lowered the y-axis 2 units. And that's how you can look at this and immediately know what the transformations were without having to go through all this process every time. Now let's do a final check. Let's take this and graph what we have here. So this is going to be 3/2 multiplied by the square root of negative parentheses x minus 5, and we'll put a -2 at the end here, and that red graph is approximately what we have. We've taken the x coordinates and made them negative, so we've taken the graph and flipped it over the y-axis. Then we've stretched out the verticals by a factor of 3/2, which is a little bit hard to see here, but we've made it taller. And then we've moved to the right 5 and down 2, all packaged in this right here. All right, let's return the discussion to functions. So here on the screen, we have a graph of y equals g of x. You can see that up there. Then we're going to take that and transform it according to these steps. So first, we want to reflect across the x-axis, which is going to flip our graph upside down. So that's a vertical dilation of times -1. Then if we do another vertical dilation of times 2, the combination is a vertical dilation of times -2. Okay, so we'll do that in one step. And then a horizontal dilation of times 3. We'll stretch it out that way, and then we'll shift the origin to the left 1 and up 5/2. So what we want to do is we want to go over 1, up 5/2, maybe around there, and we want to construct a brand new coordinate system using capital X and capital Y. So for the capital X coordinate system, we want a horizontal dilation of times 3. So we'll say for every 1 unit along this brand new axis, we would have a 3-unit gap down here. So this would correspond to a 3-unit gap in the original lowercase x. And then I guess I'll go over here. This is going to be -1 and then -2 over here. Okay. Then along the y-axis, I wanted to point downward for the capital y-axis because of the reflection. And then a vertical dilation of times 2 means for every 1 unit of this new capital y-axis, this is 1, 2, 3, in the opposite direction, -1, -2, I'm going to have a gap of 2 along the original lowercase y-axis, hence the vertical dilation times 2. Now, our goal is to take this relationship and reproduce it in the capital X, capital Y coordinate system. So let's imagine. So the origin here will end up there, and then I'm going to go over to 1, 1. So I would go 1, 1 over here, and then I would go to 2, 0 right there. 2, 0 right there. This is going to be that. Okay. Then if I go backwards, -1, +1, that would be over here. And then at the top, -2, +2, -2, +2, right there. I would have this shape. So it looks like I've flipped it upside down, then I've stretched it twice, then I've stretched it 3 times that way, and I've moved it left 1 and up 5/2. Now let's do the math. To do the transformations, lowercase x, since we've stretched the x-axis out 3 times, I'm going to take capital X times the gap of 3. 3 times capital X. But since I've moved my origin to the left 1, that point is -1. I can write this -1, +5/2. I'm going to subtract 1 from the x-coordinate. To get the lowercase y, I say, well, I took my capital Y's, and I'm going to multiply by 2, but then flip them. So -2 times the capital Y. And then I've moved my origin up by 5/2 units. This is plus 5/2. Now, my goal is to make an equation capital Y equals g of capital X. How come? Because I've taken the relationship between X and Y, and I've produced that in my red coordinate system, and by doing this, I have transformed the graph by the same logic that I've transformed my X and Y axes. So we're going to cheat a little bit, and we're going to take this, and we're going to substitute this right there. How come? Because ultimately our goal is to get lowercase y equals. Okay, so we're going to say lowercase y equals -2 times g of capital X plus 5/2. So we notice outside the function, I'm doing a multiply by -2, that's the dilation, and add 5/2, that's the translation. So everything looks in order for the y coordinate. And then I would like to swap out the capital X in favor of lowercase x. So the way I'm going to do that is I'll solve for capital X, which means I add 1, lowercase x plus 1, and then I'm going to divide by 3. This is going to be capital X. So then I will take this and substitute it right in there. So this is going to be y equals -2 g of, big parentheses, 1/3 lowercase x plus 1, big parentheses, plus 5/2. Now, you'll notice that inside here, the plus 1 makes you shift to the left by 1, and the divided by 3 makes you stretch out 3 times. So the math in here, it almost looks the opposite of what you're doing. And that's what I want you to remember. The stuff in the parentheses, that's the input. The numbers look like they're doing the opposite of what the graph is doing. But outside, the numbers look like what the graph is doing. So finally, let's actually graph this and see if it comes out right. So we're going to say y equals -2 times g of, no caps, 1/3 times x plus 1. And then put 5/2 on the very outside. And let's see, does that match what we did? It does indeed. See, the origin moved from 0, 0 up to -1, 5/2, and then I've stretched out everything 3 times horizontally, 2 times vertically, and I have it flipped upside down. We have success. All right, here's the final recap. So if you want to take a graph, y equals f of x, and you want to transform it according to these. If you want to do a vertical dilation, horizontal dilation, and if these numbers are bigger than 1, that means you're stretching. If these numbers are less than 1 but positive, that means you're compressing. And if you want to reflect, you just put a negative sign in the appropriate place. And for translations, if you would like to go left instead of right, you would just make c a negative number. If you want to go down instead of up, you make d a negative number. And this is what happens. You're going to have y equals, and then inside the f, the input, we're going to have 1 over b times x minus c. So this looks like it's doing the opposite of what it actually is, so remember that. And on the outside, I'm going to have times a and then plus d. And this is how we transform graphs of functions. This is the kind of thing where the more you do it, the more physical intuition you gain. So I would say do a lot of problems, and eventually, the more you do it, the more it makes sense. Thanks for tuning in. Take care, and I'll see you next time.